Hi everyone. In the next few minutes, I will talk about the rule-based search, a new innovation by ChemAxon. First, I will talk about the motivation. Why do we need that? Because we are very good at building search engines already. There are new and growing combinational libraries coming with a huge number of structures, billions or trillions of structures. The DEL technology makes available to create these large structures. And although you are able to store them in a traditional way by enumerating that number of structures, it will cost very high, and the search speed can be still very low if you add new structures. The typical input data, so what are the rules that we are talking about as rule-based search? So they are usually based on reactions. We have a reaction center, which is usually a very simple one, and there is a list of reactants, not that huge, with not that huge size, so it's usually less than 100,000 structures. So it's in the normal range to handle. They can, or sometimes they are also represented as a Marquis structure with the simple scaffold and R groups. We are talking about the same thing if you think about that. We've got two example libraries that we were working on. This is the first one with 7 million structures. Here you see the reaction center, which is a simple one, and 3 R group positions, less than 200 structures or R groups each, but still they together combined create 7 million structures. So you can see that by only a few definitions, you will get a lot of products at the end. Another example library based on a reaction, we've got only 40,000 reactants for each position. That is not much for a search engine, but together the 1.6 billion structures, yeah, that's very, very large. So we wanted not to store all the structures, but only the reactants and the reaction center, and do a search based on them. So when we are searching on a data set like this, we are searching always on the product space, the whole product space. And the important search types are substructure and similarity. These are the most relevant ones. And we need some kind of sorting method because we don't want to return all the structures. It doesn't make sense to, for example, from the 1.6 billion structures to return, let's say 1 billion. It doesn't make sense. You just want to see a few, 100, 1,000, not more. But these should be the most relevant ones. So that's the aim here. And usually we don't want to combine it with other conditions like in a relational database. Just go for the most relevant structures here. And our proof of concepts that I will demo today, we've got 3 of them because they are based on different technologies. I will show them one by one. The first is a lead-to algorithm that was not invented by ChemAxon. We just implemented. It's a similarity-based algorithm. You can use it. We used it with a chemical hash fingerprint to sort, and it's based on combining only the most similar reactants. So not all of them, just a few segments of them, which make the most similar products combined. The next algorithm is based on Marquis analysis. it's also a similarity algorithm, and the sorting method is different here. The maximum common substructure. It was developed by ChemAxon internally, the whole algorithm, and it is an enumeration of the Marquis structure. Just it's directed in a way that we go for the only for the enumerants that are the most relevant for each enumeration set. The third one is a substructure algorithm, and the key point is that the sorting is based on similarity, the chemical hash fingerprint similarity. So you get the most relevant hits here as well. It is also invented by ChemAxon, the whole algorithm, and as far as I know, nobody ever managed to make a substructure search in a rule-based data set. It's based on slicing the queries to some small fragments, and each of the slices are substructures for each reactant position. So it's again a very different algorithm from the previous two. And we've got a demo server, a Marvin Live demo, because Marvin Live is a good tool to demo these products, and it is working on a single instance. So on a very small, it would even work on a laptop as well. So let's see the demo now. So I hide myself for the just to see the whole screen now. This is Marvin Live, and you can draw your structures here. First, I show you the leap-2 similarity that you see on the right side, and when you draw your structure, in a few times you will get the results on the right side. You can set which reaction do you use or which kind of rule-based set. We've got 1 and 2. You can use them separately, like you're searching on one set or on another, and you will get the results according to that. And you always get the most similars first, according to the leap-2 method. And we show the first 10 structures. You see a very small duration. The drawing of the molecules here takes more time than the search itself. So this is one type of search, and we've got the other methods as well. We've got the MCS, the Marquis analysis-based search as well. It takes a bit more time, and it gives different results. And I suggest trying them out to see which shows better hits, which is the better similarity algorithm in your case. You can set the reaction here as well to search on, and the third one is just like the same. I will show it if this finishes. It takes about 9 seconds. I close this, and now I add the substructure search. And the substructure search has other options as well. We've got a not sorted one. This is probably the less interesting. There is a one that is by relevance, so the hits are sorted by relevance, and it's a perfect relevant calculation. So it's the same as if you enumerated the whole structures, and sometimes it's slow. Now it's 5 seconds. It's still easy to wait for that, but for some reason, for some cases, it might take longer time. The hit as you draw feature. So as you draw, you get the results without any clicks. It works here. So if it takes too much time, there is an estimated relevance which combines the quickness of the not sorted case with the relevant sorting. So it's sometimes somewhere in between, and these hits are also are superstructures of the original query that you draw, and you can draw your query as you want. Sorry, I wanted to draw it like this, and soon you will get the hits. Oh, no hits here. Anyway, it is a perfect start to try it out on this demo page, and please just contact us to try it out with your data as well. So that's the demo page, and let's go on with the presentation. And if you liked our demo and you were interested, here are the algorithms. I've got a few more slides for the algorithms, which I won't show you now. Just pop it up if you are interested. We can talk about it, or you can speak with us about them later. We've got some measurements for each of the demoed algorithms. So we are still looking forward to working together with you in improving this, and we are very curious how it would work with your data, not just ours, but yours as too, because it can be different. So it would be very interesting to see if we can get the same results with your data. And I want to highlight that Meg McCarrick will have a nice presentation tomorrow about a similar topic, the virtual libraries. There are some overlapping with what I demoed, but it's from a more scientific viewpoint. So I advise you to stay for that as well. And thank you very much.